In the last video, we had seen how we could calculate a scatter plot in Excel, and that worked fine as long as we only had a single column for our explanatory variable and another column for our dependent variable there, the response variable. Maybe our textbook calls this independent and dependent. Also, you have explanatory and response. That works quite fine when you only have two columns worth of data. But as we had discussed at the end of the FaceTime video, where I guess not FaceTime because that's iPhone, but when we discussed when I was talking to you face to face, sometimes we like to be able to try to get a better accuracy rate than what we had. So it becomes important to be able to add more columns, in which case we no longer have bivariate information, instead we have multivariate information. In which case it becomes very difficult to create a scatter plot because suddenly you're talking about 3 or even more dimensions. Still, we can find some relationship between what we did before. So if I click on this data column again and click on data analysis, I can scroll down in this list of information here until I find regression. We can hit OK. When I do that, I can input my y range. I can input my x range, our independent variables. I can tell it that I have labels in that first row so that I don't accidentally try to calculate things on there. And we could even pick a confidence level. Our textbook often uses a 5% alpha, so 95% confidence level. And I can even highlight an area inside our data sheet to put this information so it doesn't open up a new worksheet ply. And there would be other calculations we could do, but this will be good enough for us at the moment. When we hit OK, Excel gives us a great deal of information very fast. But still, I want to show us that some of it is familiar. And again, I'm taking my little cursor and sticking it over the columns and double-clicking so that all of these words here become large enough that I can actually read everything in each one of the cell files. Notice here this p-value is given to us in scientific notation. If I select it and click on Home, and then if I select here and I can just tell it that we want this information in number format, and then we can increase the number of decimal places, and then you don't have to worry about trying to translate scientific notation perhaps. Some things to recall and think back on that maybe we saw before and were expecting. Remember our formula. It was ax plus b, and this was the number in front of the x. This was the first value, and then this was our second number. I think we had rounded those on the whiteboard down to 2 decimal places. And again, I could use the decreased decimal place feature of Excel to make that rounding happen, and then those would be the familiar numbers we had looked at. We had also talked about the r squared number, and of course we had also talked about our r value, and those two numbers are showing up here. So things we've already seen before in 2 variables we're already seeing. These are the parts that perhaps are interesting to us. And if you had taken a look at your textbook, we might have been also interested in calculating the t-statistic, which I'll talk a little bit more in another video, but that p-value that we'd be interested in finding that we've been used to from hypothesis testing, we're very interested in that, and that p-value is also right here, that it can talk about us with things. So your Excel is maybe even more powerful than just our calculator because it can calculate so much for us. So much for 2 sets of variables, a single explanatory variable and of course a single response. Let's take a look at sheet 2 here. Sometimes maybe we want to call sheet 1 bivariate data, in which case sheet 2 would become multivariate. And now we have something different because we still have our hours per week, we still have our score, but now perhaps we have the years since the last math course. And if this years since the last math course is in here, our hope is that, remember, when we were back here in the bivariate data, let's go ahead and take a look at our scatter plot one last time. Highlight that, go to Insert, and stick that scatter plot back in here. And we had done that, and when we had done our trend line and asked it to display the equation and that r squared value there on our chart, notice I can drag this around and make all the pieces that I want here fit. So here's our equation. Notice here is our coefficients that come from each of these pieces of this equation. I can go ahead and select these and maybe take it out to 4 decimal places, which is what we seem to be having here in our equation. So you can see exactly where we're getting all this information. Here is the r squared value. Again, that seems to be going out on this scatter plot line to 4 decimal places. So you can see exactly where all of this information is coming from in the more powerful Excel calculator than just a single scatter plot. And what you notice in here as we did this is that our r squared value, and r squared was very interesting to us because we had some interesting interpretations for that. In particular, we like to say that r squared was the coefficient of determination, and the way we understood that is that the r squared value is a ratio of our explained variation divided by the total variation. In other words, it's the amount that this model improves us on over just a single point estimator, perhaps. And so that meant that we had about 19% of our total variation in our data could be explained by this model. And I said that in some disciplines, such as medicine, maybe very, very small r squared values are of use. And in other disciplines, maybe we're normally expecting numbers that are a little bit higher than 0.18. In education, if we're talking about student scores, I would kind of like to see a number a little bit higher than 0.189. So let's go ahead and look at multivariate data. We've got, what we do is we create just a little bit more. We create an extra set of things that become part of our explanatory variables. So not only do we talk about the hours per week the students spend, but we also talk about how long it is since they last practiced mathematics before coming to this course. And if we take a look at this, well, now we can do something. Let's go ahead and go to Data and Data Analysis and keep on with this idea of regression. We'll hit OK. But now our input y variable is this last column C. The response stays the same. We just want to predict it a little more accurately. So now when I go to this input x range, we're going to select both hours per week and years since last mathematics course. So we get a little bit more information here. Still have labels, still confidence level of 5%, and our output area can still be the same place where it used to be. And now we can hit OK. And again, I can get my little mouse cursor here, and we can make things a little bit larger so that we can actually see some values and read them off a little more clearly. We'll continue to use more and more of the numbers on this chart, but I'll continue to talk about the ones we're interested in. Still, these two values right here, it might be interesting to go to home and convert them out of scientific notation. And again, add ourselves some decimal places till we can see what those values are. All right. Possibly here we want to convert this also out of scientific notation. We'll convert that into a number. Notice our coefficients have changed. We don't have the same coefficients we had before because now we've got a 3 column model. 2 of our columns here, if I wanted to insert a row here, we could label these ones as our explanatory. Apparently I can't type today. This is our response variable. Also, I think in our textbook we call these ones the independent and this one the dependent variable. Well, now we have a little bit more power behind our model calculation. In the previous section, we had these as our coefficients, and if you wanted to create a formula, we would have said that formula was going to look like, if we had an x value that we wanted to input, and maybe I had done on the board, I think, an example with 4 hours a week of study, then our y hat output that we would have expected would be our hours per week times the x value plus that intercept. Let me go ahead and make sure that I've got some decent parentheses around all this. And this then would be our prediction for what we would think our score might be. If we study 4 hours per week, the line's going to make a prediction of 0.75. And you can see that point there on that line. But now, back then we only had a 19% R squared, a 0.19 R squared, and so maybe that wasn't all that powerful. So now, if we go ahead and take a look at our multivariate data, you see that we have a much higher R squared. That's very high. This years since the last math course is able to predict almost all of the variance. Now this example here has actually gone from something that's pretty legitimate, where I generated it with very real numbers, and for this multivariate, because I wanted to make a big jump to distinguish this, this is actually a little bit artificial. I rounded all this data up to the nearest year. But now we have a much more long model. But let's take a look. Still, if we wanted to calculate an x, and we could plug in the number 4 there for that, we would also want to figure out what our y hat was. Now our model gets a little more complicated, because we have to do more than just plug in an x of hours per week. We also have to plug in, so sometimes we call these ones x1 for the first one, and x2 for the second, and then we can have y hat, where x1 is going to be hours per week, x2 is going to be years since last math, and so now we'd have to type in more information. And let's take a look at how that will look in a second. And then our y hat would be based on, well, we're going to have our years since our last math course times however many years that is, plus the hours per week that we spend, coefficient times the actual hours per week that we spend, plus our intercept. And so if it's been 0 years since our last math course, we can see that we have ourselves a prediction of 4 hours a week should get us a B. But if it's been 1 year since our last math course, suddenly 4 hours a week really isn't enough. And if it's been 2 years since the last math course, it gets even lower. And if we get very many hours per week since our last math course, very many years since the last math course, it goes even lower. And the beautiful thing about this prediction formula, as we've cooked it up, is that we can play around with it. So let's say it's been 4 years since your last mathematics course. Well, maybe you need to spend 5 hours, 6 hours. Let's see how many hours a week we have to spend. Why is this not calculating like I wanted it to? Clearly, overall, the years since last math course is much more powerful a predictor of success than just hours per week. But eventually I'll find a number big enough to make a difference. There we go. Normally, we would expect maybe not quite, that this is of course impossible, right? The most you can do is 168. What you're finding is that our model here probably still isn't perfect. Let's talk a little bit about why that's the case. If you go back to the bivariate data and look at just hours per week, we'll see that this only had explained 0.189, 19% of all the variance. When I went to this multivariate data, on the other hand, we saw that we'd gotten ourselves up to 0.83. What that tells us is that this year since the last math course became a much better predictor of score overall, to the point that hours per week doesn't mean much. And we can see that here. 4 hours a week, 0 hours a week, 168, the maximum hours a week you could possibly do. It all keeps on being the same. It's all about the years since the last math course. And that makes sense, because if I look at 83% and subtract the value in that first sheet, you can watch how I just did that there, and I then hit enter. You'll see that the majority of all of the explained variance that we're able to cope with in our model is probably coming from this next column. And I've done this a little bit roughly, and maybe I haven't quite done it right, but maybe this is good enough to see where these pieces are coming from. Now, of course, as I said, this is a little bit artificial. And notice both the ways that our model is good, it's given us a pretty decent prediction level, and the way our model's bad. Notice as we play around with these numbers, it doesn't perfectly predict the way we would expect the real world to work, right? Because, of course, if you just took a course before this one, suddenly it's been 0 years since your last math course, right? And so you would expect this to go up quite a lot. I don't know. So then you would go back down to 4 here. Whereas if you haven't taken a course since this one, you expect this number to be a little worse. But a course is only 48 contact hours. So if you were to take 48 contact hours, multiply it by the 3.5 I recommend students to do, really you should be able to get all the benefit of having had a math course before this one, right before this one, in 168 hours. So I would really expect that if you were spending 60 hours a week on just this course, we should see quite a bit of improvement over that 62%. Which is always why, of course, you have to use common sense, and you also have to be very careful that what you're trying to use your model to analyze is within the right range. And also, you should make certain that you don't include things that are kind of worthless anymore. Rather than try to cope with hours per week in our model, what we should really do is say, look, if it's been 1 year since your last math course, we expect you to probably be inside the C territory. But if it's been 2 years or 3, you start to be at a disadvantage. And that means you're going to want to spend extra hours per week to try to fight that disadvantage a little bit. So this is multivariate data now that we've done. We had bivariate with just these 2 columns, and that was nice because we could do scatter plots. Now with multivariate data, maybe we can't do that so much. Notice that this r-squared value is very high. Remember, it lives between 0 and 1, and 80.83 is very, very, very high for multivariate explanation. Normally, I would say that we would be perfectly happy with normally we'd be very happy with a much lower r-squared. And we'll see some more examples of that. I'll try to find some more real-world examples that make this happen. But now you can see the techniques for using Excel to do bivariate data and multivariate data. And also, of course, we can also see the p-values already calculated for us. So that makes it, in our textbook, when we start talking about hypothesis testing with linear data, we are able to calculate that out as well and see that right here in Excel. So I'll do an example now that maybe ties it all together in the same steps that our textbook is talking about, and we'll have that